We begin with Unit 1, Biological Molecules of Cambridge AS Level Biology. We're going to start with the properties of water. Now, normally I begin my course by showing a video from Crash Course by the Green Brothers, but they're not paying me, I'm just a fan. Water's bond angle, some of the things that are associated with this. Water's bond angle is 104.5 degrees, and methane's bond angle is 109.5 degrees. This results from the repulsion of hydrogen from unpaired electrons in the oxygen. So that forces these hydrogens together, decreasing the bond angle. But in methane, we have equidistant hydrogens, which all have the same bond angle between all the angles, and that is 109.5 degrees of angle. This is 104.5. Now this disparity has a lot of added benefits, including this particular shape of the solid water crystal, aka ice, which we will discuss in a moment. So, a quick question about definition. Which term describes the heat absorbed when a substance changes phase from a liquid to a gas? Enthalpy of vaporization, latent heat of vaporization, heat of evaporation. The answer is all above. Cambridge will call it the latent heat of vaporization. So, the specific latent heat, which is what you will be tested on, the specific latent heat is L. It expresses the quantity of energy in the form of heat Q required to completely affect a phase change of a unit of mass N. This is usually 1 kilogram for all intents and purposes. That's what you'll be working with. Of a substance, this is an intensive property. So LF is Q over M, and LV is Q over M. That is your latent heat of fusion and your latent heat of vaporization. The latent heat of fusion is the energy required to be removed from the liquid in order to change its phase completely from liquid to solid, or the energy that must be added to the solid to completely change its phase to liquid. During this time that you are adding energy and changing phase, the temperature of the water is not changing. From liquid to gas, we have the latent heat of vaporization. So we must add energy. We must add heat in order to go from liquid to gas to completely affect a phase change. So as water is boiling, we are adding heat energy, but we are not affecting a temperature change. We are only affecting a phase change. All of the energy going into the water is changing the water's phase, not its temperature. So that's the point of latent heat. Specific latent heat. And gas, in order to remove all of that energy, when we remove that energy, it will condense to liquid. So, vaporization, the latent heat of vaporization, is the change from liquid to gas and back. The difference is only a negative symbol or a positive symbol. Alright? So these are intensive properties. An intensive property of a material is a characteristic that is not dependent on the size or the extent of the sample. Commonly quoted and tabulated in the literature are specific latent heats of fusion and the specific latent heat of vaporization for many substances. So, how much energy is required to change its phase from solid to liquid and from liquid to gas, adding heat, that is often tabulated as an intensive property of that substance. So, how do we calculate the latent heat for a given mass of a substance? All we need to do is we need to change what we want to the other side of the equation. So if latent heat of fusion or vaporization is on one side of the equation, and latent heat and the heat is on the numerator and the mass is on the denominator, we want mass over on this side alone. We need to multiply, I will use a different marker, we will multiply by mass both sides. That will cancel out our mass, and we are left with heat is equal to the latent heat multiplied by the mass. Now we want mass by itself. We will divide both sides by the latent heat of fusion, or the latent heat of vaporization, and that will leave us with mass is equal to heat over latent heat of fusion, or mass is equal to heat over latent heat of vaporization. This is mere algebra. We are just moving variables from one side to another in order to find what we want, so we can make our math easier. That's all we need to do here. So that's how we would calculate it. And that's all that I'm doing here. To find my latent heat, Q, the quantity of energy released or absorbed during a change of phase in the substance. M is the mass of the substance, and L is the specific latent heat for a particular substance. Therefore, Q equals ML. Q equals LM over here. It's only part way of the movement of the variables that I did before. So either for the latent heat of fusion, LF, or the latent heat of vaporization, LV. Now, we have some other terms to define. Those other terms to define are the latent heat of fusion. While it's tempting to say the latent heat of fusion is the opposite of the latent heat of vaporization, this is wrong. It's how much energy in the form of the heat is required to change the phase from liquid to solid, or to fuse a liquid into a solid. Specific heat, or heat capacity. This is how much energy a substance can hold before it changes temperature. The exact mathematical definition is Q is equal to mass times the specific heat capacity, C, times the delta T, the change in temperature, which is in Kelvin or degrees Celsius. Now, latent heat of fusion and latent heat of vaporization, these apply to changing phase. Specific heat and heat capacity, which are the same thing, they apply to changes in temperature within a phase. So, heat capacity is the resistance to a change in temperature while the substance is still a liquid, for example. So, after it has completely changed phase from solid to liquid, and from before it has changed phase from liquid to gas, adding heat energy will get you a temperature change. How much heat energy you must add in order to affect that temperature change, that is your heat capacity. Now, more definitions. Hydrophilic and hydrophobic. Polar and nonpolar. Charged, ionic, and uncharged, non-ionic. Water-soluble and water-insoluble. Lipid-soluble and lipid-insoluble and lipid-soluble. These definitions go hand in hand, as do these. These tend to be the opposite of one another, as you can tell from polar and non, charged and un, water-soluble and water-insoluble, etc. So, hydrophilic, water-loving in Greek. Hydro, water, philos, love in Greek. So water-loving. These will dissolve in polar molecule, in polar solvents like water. Hydrophobic, phobos, fear. Hydro, water in Greek, all Greek. So this is water-fearing. These substances will not dissolve in polar substances like water. So hydrophilic substances are polar because like dissolves like. Hydrophobic substances tend to be nonpolar because like dissolves like. If they are nonpolar, then they will tend to dissolve in nonpolar solvents. If they are charged or ionic, they will be polar, almost by definition. If they are uncharged or non-ionic, then they will not be polar because there will be no differential charge as a general rule. Alright? So, water-soluble is similar to this hydrophilic, and water-insoluble to this hydrophobic, but that's specifically for referring to water, not just polar substances. Lipid-insoluble, lipids tend to be non-polar across the board. And lipid-soluble, they are soluble in lipids, in non-polar solvents. So you can dissolve a substance in water, but you cannot dissolve it in oil. You can dissolve a substance in oil, but you can't dissolve it in water. This is the case for many different compounds, depending on their nature of polar versus nonpolar. So, the key concept about the properties of water for the ACE exam is polarity. This is what accounts for water's ability to dissolve polar and ionic compounds and adhere to surfaces, and thus capillary action, to cohese to other water molecules, and thus its surface tension, and results in the geometric pattern upon freezing that gives the solid form of water a lower density than the liquid form of water. So let's talk about water for a moment. The overall formation, actually let me just do this in different colors to make things easier in my life. I will make oxygen red because convention. I will make bonds black because convention. And I will make hydrogen blue because convention. So now we see that we have this positively, let's say this differently. Oxygen is a highly electronegative element. Highly electronegative elements have a desire to attract electrons. They really pull on those electrons. Hydrogen is a weakly electronegative element. That means it will give up its electrons readily. It will readily give up those electrons. So when you have a covalent bond, the covalent bond is the result of a shared electron pair. Hydrogen donates one electron, oxygen donates one electron to this covalent bond, and the same goes for here. Because oxygen is more electronegative than hydrogen, the electron pair will be closer, and it will spend more time with the oxygen than with the hydrogen. This allows the oxygen to have an overall negative charge, delta negative. And because of that, we have the orbital cloud being pulled away from the proton that is the hydrogen, and we have an overall positive charge, delta positive. We can place this with an arrow diagram like so, showing the overall dipole movement here. So we have positive charge in the hydrogens and negative charge in the oxygen. This is the beginnings of hydrogen bonding. Hydrogen bonding is the most important concept in the properties of water. This is what causes all of this. This polarity allows for hydrogen bonds. And if you are asked any question about explain why this is occurring, the answer in water, it is most likely because of hydrogen bonding. So, when you have an oxygen molecule here, and I've given up using the red because the red pen's all the way over there, all right? And you have a hydrogen over here, and you have a hydrogen over here, and an oxygen over here. Yes, I know the oxygen and the hydrogen are different sizes. I didn't say I was a great artist. The positive charge of this side to this side will attract, the negative and the positive poles of these molecules will attract one another, forming a hydrogen bond. An oxygen atom on water, can form one hydrogen bond with the hydrogen on another water molecule. So one oxygen can form one hydrogen bond. So the ability to form hydrogen bonds is extraordinarily important. So what you end up with, and by the way, hydrogen bonds are always drawn as dotted lines. They're always drawn as dotted lines by convention. That is always going to be the case. Hydrogen bonds are dotted lines, and if you were asked to, we have the hydrogen bonding here and here, dotted line, to oxygen over here, hydrogen bonding over here. All right, this is our hydrogen bond. We can cut that together later. So this hydrogen bonding is what allows any of this to happen. For example, it allows for this is cohesion. This is what allows cohesion. What allows water to bind to and be attracted to other water molecules. That is cohesion. This is also what allows water to dissolve chloride ions. I did that backwards. Sodium ions to the negative end, or chloride ions to the positive end. With this hydrogen bonding going on here, more oxygen over here, more oxygen over here. So this hydrogen bonding to these ions, that's what allows for the dissolving of polar and ionic compounds. We also allow for adhesion, which is water and, let's say, an amino acid, which would be nitrogen and hydrogen. This would be positively charged over here for our amino group. There's our alpha carbon, which we'll discuss later. There's our R group. There is our hydrogen down here. There is our carboxylic acid group, our double bonded oxygen, and our unbound hydroxyl group, which has lost its hydrogen, it's donated its proton already. So our water over here allows for that bonding to occur. So we have proteins over here. We can have protein chains, the terminal amino end, the terminal carboxylic end, excuse me, or the terminal amino end. Or if the R group is charged, we can have hydrogen bonding there. That will allow for adhesion. Surface tension. Surface tension is the result of water molecules being more ready to cohese to each other than to the air around them. They will more likely be with each other than they will with the rest. They will be more likely to hydrogen bond to each other than with the nonpolar atmosphere, resulting in surface tension, which can form water into a droplet formation. When water freezes, there is a lattice structure of water, hydrogen bonding to other water molecules. So the dipole moment of oxygen being negative will repel other oxygen molecules. The dipole moment of the hydrogen being positive will repel other hydrogen molecules. This will result in a crystal lattice, a separation of these different charges and expanding the molecule as temperatures decrease. As your kinetic energy decreases at lower temperatures, the interactions between the polarity, the positive and negative charges of these water molecules will take over, and you will have charge repulsion being the more dominant force than kinetic energy slamming one molecule into another. So the density of water will decrease past 4 degrees Celsius, from 4 to 0. 4 degrees Celsius is the densest liquid water will be. The densest any form of water will be. So anywhere from 4 to 0 degrees Celsius, Liquid water decreases, it goes from 1 gram per cubic centimeter to like 0.998 grams per cubic centimeter. But as soon as it hits frozen solid water, it goes from 0.98 to like 0.91 grams per cubic centimeter. It goes to like 9-ish, 10-ish% less dense. So ice will float. The freezing geometric pattern gives the solid form of water lower density than the liquid form, and ice will float. And ice is a good insulator for heat, so when ice floats, it will form a layer of ice, and you'll have a liquid water layer underneath, and if the means by which you lose heat is through the surface of the water, then that means you can't lose heat through the liquid water to the surface because there is a layer of ice between you and the surface. So that's why building an igloo will keep you relatively warm, why you can go ice fishing and still find anything but fish sickles in the water underneath, etc. Now, we'll move on from water for a moment and discuss macromolecules. I'm going to give a brief overview. First, let's talk about what a macromolecule is. Macro is large, molecule. A macromolecule is a very large molecule that is commonly created by the polymerization of smaller subunits. They are typically composed of thousands or more atoms. Let's briefly discuss the function of each of the primary 4 types of monomers. Type 1, carbohydrates. Carbohydrates are things like sugar and fiber. Lipids are fats, oils, waxes, and steroids. Hormones like testosterone are also lipid-based hormones. Amino acids are proteins, enzymes, and hormones are what amino acids build. Amino acids are the building block of these larger macromolecules. And then we have nucleic acids, which are the building blocks of DNA and RNA. So, a carbohydrate will generally have the structure of CH2O, the formula, not the structure, excuse me. We generally have the chemical formula, the empirical chemical formula of CH2O. We have a problem. This is formaldehyde. That's not particularly tasty. That will make you go blind and, well, eventually crazy and stupid and kill you. So, formaldehyde is a problem. But it is technically a carbohydrate. So what we're primarily going to be discussing is we're going to be discussing sugars, which will have a basic chemical formula of C6H12O6. This will be our glucose, our fructose, our galactose. Fiber is typically, when we discuss fiber, we're going to be referring to cellulose, which is a chain polymer, a single chain polymer with no branches of glucose. Beta glucose most typically. That's usually what we'll talk about when we discuss fiber. Now, lipids, our fats, our oils, our waxes, they're going to be primarily hydrocarbons. Carbohydrates contain carbon, hydrogen, and oxygen. Hydrocarbons will typically just be carbon and hydrogen. So CnH2n will be our typical 2n plus 2 will be our typical chain form of just a straight carbohydrate, just an alkane, for example. But oils, fats, these are all going to be long chains of hydrocarbons. Waxes are going to be the combination, the ester combination between 2 different fatty acids or oils bound together at their heads. Steroids are typically going to have a tetracyclic structure, which means a 4-ring structure. And hormones like testosterone specifically, has a tetracyclic ring structure. It is a steroid hormone. Cholesterol is also a steroid compound. Now, amino acids. Amino acids will typically have a similar function that I described before. You'll have your amino group, which will be your amine. So this will be NH3 positively charged, moving to an alpha carbon, which will have a hydrogen and a R group, which can be variable. And then you'll have your carboxylic acid group, CHO minus. Now, the uncharged version of this is to remove the hydrogen and add a hydrogen over here. So this is just carboxylic acid and an amine group over here. All right? So this is your basic structure of your amino acid. Chaining these in sequence from amino to carboxylic, amino to carboxylic, amino to carboxylic, carboxylic, that will get you your polypeptide chain. Proteins are polypeptide chains. They have a bunch of different forms, but enzymes are proteins with a job to do, and hormones can be also in protein form. Insulin, for example, is a proteinaceous hormone. Nucleic acids. Nucleic acids will typically have the structure of a phosphate group, a 5-carbon sugar, a 5-carbon sugar, and a nitrogenous base. So that will be your typical structure of your nucleic acid. Nucleic acid, or your nucleotide, excuse me. Nucleic acids are the long chain forms of DNA and RNA, which are composed of many nucleotides. So, this is oversimplified for now, but let's talk about our most important chemical reactions in Cambridge, the condensation reaction and the hydrolysis reaction. Yes, this is blurry. That's not the camera. That's actually the slide. It is actually blurry on the screen. So, in our condensation reaction, we have 2 sugars, 2 carbohydrates that undergo the condensation reaction. Water is removed, and a glycosidic bond will form. In our hydrolysis reaction, or our hydrolytic reaction, we will have 2 sugars that are bound together as a disaccharide. Water will be added. This disaccharide glycogen bond will be broken, and you will have, at the end, 2 separate monosaccharides. This reaction, these 2 reactions, can apply to any macromolecule. Remove water to create and to form a bond. Add water to break a bond. When you are doing this, it is important to redraw the structure of whatever it is you are drawing. So, if I am going to do this, I will redraw the structure. Here, I'll draw this, I'll draw this, I'll draw this oxygen here, I'll draw this carbon over here, I'll draw this carbon over here. This is CH2OH. This is going to be our hydrogen. Oops, that looks terrible. This is going to be our hydrogen over here. This is going to be our hydroxyl group over here. This is going to be hydroxyl. This is going to be hydrogen. This is going to be hydroxyl. This is going to be hydrogen. This is going to be hydroxyl. This is going to be magic, and we've completed this. Note the positions of the hydroxyl groups down here. We have glucose, we have fructose. For our condensation reaction to take place, we are going to circle the 2 hydroxyl groups that will interact. And this is what you do on a Cambridge exam when you're answering a question like this. These 2 hydroxyl groups will interact. In fact, you're actually going to specifically circle the hydrogen and the hydroxyl group that will interact. You will show water leaving, H2O, and then you will make the arrow that moves to the side. And here we go, drawing the rest of the frickin' molecule. All right, H, O, H. I'm going to shorten this because I don't want to redraw all of this. Now, on the Cambridge exam, you should absolutely redraw all of this, but fine, I'll redraw all of it. Why not? I'll be a good role model. H. Okay. All right. So we have here our glycosidic bond, and if they ask you to label, that's your glycosidic bond. So if I want to label this, I'm going to label that as my glycosidic bond. All right? So I have shown the interaction between the hydroxyl group of fructose and the hydrogen of glucose, and the resulting leaving of water. The resulting molecule is sucrose, which is the combination of glucose and fructose with a glycosidic bond formed plus H2O. Forgot that before. Whoops. Plus H2O. Now, the reverse reaction. If I'm going to do this, then I'm going to erase this stuff. All right? I'm going to erase this part. I'm going to show water, the hydrogen interacting with this, and the hydroxyl group interacting with this carbon. And then that will result in this here. So this water will break apart. This hydrogen will be added to this oxygen. This hydroxyl will be added to this sugar. Now, there is a little bit more to that in terms of the movement of the unshared or shared electron pairs and all that other stuff. But in terms of where you get your points from Cambridge, that's unnecessary. So, the addition of water resulting in a broken glycosidic bond. Now, this is the same. Stop the recording?
No. I can't tell if you're going to move on to the slide or not.
Well, I was. Might as well stop the recording now. So, this condensation and hydrolysis reaction. So this condensation and hydrolysis reaction works no matter what the molecules are. It works no matter what the starting molecules are. This could be an amino acid, glycine and lysine. It could be the glycerol and the fatty acid. It doesn't matter. Condensation reaction to form a bond and hydrolysis reaction to break a bond by the addition or subtraction, the reverse respectively, of water. So the removal of water to form a bond and the addition of water to break a bond, this is true no matter what molecule you are dealing with. So possibly helpful terminology, by which I mean absolutely useful terminology, conformational isomers. So when we're talking about carbohydrates, we have our chair form of glucose, because it looks like a lawn chair. We have our boat form, which is an unstable intermediate form, because it looks like a boat, or some organic chemist thought it did anyway. I'm not sure quite what they were thinking, but okay. And then that results in, this can flip down, and we'll have the reverse of the chair form. It's the chair form all over again on the other side. No bonds have changed. No bonds have been broken. No bonds have been reformed. No electrons have moved around. No shares of electrons, no pairs of electrons shared. No pairs of electrons have been shared in any way. This is just the movement in bonds that already exist. This is just the interplay between bonds. So conformational isomerism are isomers, the same molecule that takes on different shapes because it can conform to fit a different shape. You can just fold it. Click, 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 click. You just move them. Now, naming of carbohydrates, we have a very simple naming scheme. It's based on Greek. We have how many carbons? How many carbons does it have? If there are 3 carbons, it's triose. If there are 4 carbons, it is quadrose. If it is 5 carbons, it is pentose. If it is 6 carbons, it is hexose. 7, septose, etc., etc., etc. So on and so forth with the Greek name, all the way to dodecatose. All right? Oh, sorry, tetros, not quadros. Quad would be Latin. All right? So, pentose, keep this one in mind. This is ribose. This is ribose, which is going to be useful for RNA. We have these 2 forms. We have the chain form and the ring form. The chain form is the form where we have our aldehyde group or our ketone group as required. And in the ring form, we have a ring. It is more chemically active in the chain form. In solution, sugar will often become the chain form, and that is how it exists and persists in an aqueous solution. So this is our hexose sugar. This is D-glucose, dextroglucose. Dextrose, for short. It consists of 6 carbons with an aldehyde group at the 1 carbon, a hydroxyl group on the right side, if you're doing it that way, on the 2 carbon, on the left on the 3 carbon, right 4, right 5, and our CH2OH, our end hydroxyl group on our 6th carbon. That carbon can rotate, so it doesn't matter where that one is. Now, we are numbering our carbons. In our ring form, we have a 1,5 ether linkage. This 1 carbon, this double bonded oxygen, will become our ether link. It will bond to our 5 carbon, the hydroxyl group in the 5 carbon position, to form our ether link. So this is what determines the ring structure. Where is that double bonded oxygen? Where is that double bond? We are numbering these carbons based on what's the most interesting group, near the end. So this is our 1, 2, 3, 4, 5, 6. Remember where they are. This is a 1,5 ether linkage because it is the 1 and the 5 carbon, and it isn't ether. carbon, oxygen, carbon. Now, this must be committed to memory. The Fischer projection and ring form structures of glucose, galactose, and fructose. They differ in a few changes, and that is all. Glucose versus galactose in the projection, the Fischer projection, has on the fourth carbon, the hydroxyl group is on the right, and in galactose, the hydroxyl group is on the left. In fructose, it is the same as glucose, only you have switched. You have switched where the double bonded oxygen is. It is, instead of on the end as an aldehyde group, it is now on the 2 carbon as a ketone. So that makes this an aldose sugar, and a ketose sugar, based on the group of where that double bonded oxygen is. Aldehyde, ketone. In the ring form, glucose and galactose look very much the same. The difference being that the 4 carbon of galactose, the hydroxyl group on the 4 carbon points up versus trans configuration, which is up when the 1 carbon hydroxyl group is down. They are opposed to one another. They are in the trans configuration. The glucose will be with both hydroxyl groups down. This will be our alpha glucose. Now, any other further differences? There really aren't. In our fructose form, by the way, this is forming a 5-sided ring, but not a 5 carbon. It is not a pentose sugar. It is still a hexose sugar because we have 1, 2, 3, 4, 5, 6 carbons. And our CH2OH groups are in a trans configuration to one another. Now, aldose and ketose, which I mentioned before, the carbon-oxygen double bond is located at the end of the carbon chain in an aldose sugar. In a ketose sugar, the carbon-oxygen double bond is located within the interior of the carbon chain. So, glycosidic bonds. A glycosidic bond is where we have, or a glycogen bond, or a glycosidic linkage. That is where we have a condensation reaction where water is condensed out, and this forms the carbon-oxygen-carbon linkage, glycosidic linkage between these 2 molecules. This is a 1,4 glycosidic linkage. It is a 1,4 glycosidic linkage because it is on the carbon 1 of the first glucose, and it is on the carbon 4 of the second glucose. Glucose plus glucose yields maltose. Alpha glucose plus alpha glucose yields maltose. So now we have an idea of our simple carbohydrates. Monosaccharides, like glucose, are just 1 carbohydrate unit. A disaccharide, like sucrose, is 2 monosaccharides bound together by a glycogen bond. So we have glucose and fructose here connected by a glycosidic bond. That becomes a disaccharide. Complex carbohydrates is a polysaccharide. A polysaccharide is when you have more than 2 monosaccharides bound together. Mono, di, poly. 1, 2, many. Now, remember that in our carbohydrate molecule, our empirical formula, or our molecular formula, was C6H12O6. In a disaccharide, where you are adding 2 monosaccharides together, you would think perhaps that it would be C6 plus H12O6, and you would just add them together, right? Wrong. That's forgetting that you are in fact subtracting water for the condensation reaction. So, C12, H24 minus 2 is 22. O12, 6 plus 6 minus 1 is 11. So a disaccharide's chemical formula, no matter whether it is glucose plus galactose, galactose plus fructose, fructose plus fructose, doesn't matter. It will be C12H22O11. Further additions of monosaccharides will always subtract water. It will add C6H12O6 and subtract H2O. So, that is how we move forward and add in the chemical formula department. So, here's our table of the different combinations of monosaccharides. When glucose and glucose get together, and they are both the alpha glucose in an alpha 1,4 glycosidic linkage, that becomes maltose. Beta 1,4 glycosidic linkage will be cellobiose. Cellobiose is a breakdown product of cellulose, which is a chain of beta glucose. Beta glucose looks a lot like galactose, but it's not. So we'll get to that in a second. Glucose plus fructose is sucrose. Excuse me. And that has an alpha 1 beta 2 glycosidic bond. Because glucose is in the alpha configuration, and sucrose, and fructose, excuse me, is in the beta configuration, and it bonds the 1 carbon of the glucose to the 2 carbon of the fructose. So sucrose is alpha 1, 2 beta sucrose. So glucose to fructose, glucose to fructose. Galactose to glucose gets you lactose. That is a beta 1,4 glycosidic bond. A beta 1,4 glycosidic bond. Glucose must be in the beta configuration. Galactose will be in any 4-carbon configuration. So, it's the same over there, glucose to galactose. Fructose plus galactose gets you lactulose. That is also in a beta 1,4 configuration, where fructose is in the beta configuration and galactose is in the 4 configuration. So, maltose is sugar, is a malt sugar, so a malt beverage, for example. Cellobiose is a breakdown product of cellulose, so what you would get when a rabbit is trying to digest its meal. Sucrose is table sugar, lactose is milk sugar, and lactulose is a diuretic, as in it makes you poop, like really badly, like a lot. So, table sugar, milk sugar, malt sugar, lactulose is used to treat constipation and hepatic encephalopathy because it is not absorbed. Cellobiose is a hydrolysis product of cellulose. Cellulose is the primary structural polysaccharide in many plants. We'll get there. So, alpha versus beta for glucose. So, here is alpha glucose. Here is beta glucose. The 4-carbon is always the same. The 4-carbon will always have its hydroxyl group down. That is in fact the difference between alpha glucose and alpha galactose. The 4-carbon in alpha glucose, the 4-carbon in galactose is flipped. In alpha glucose, it is down and 1 is down. In beta glucose, the 4-carbon, the hydroxyl group is down, and the 1-carbon, the hydroxyl group is up. How did this happen? Because the aldehyde group can turn. Because the aldehyde group can rotate, if it rotates to the other side when it forms that ring structure, then the hydroxyl group will be upside down versus right side down. Will be right side up, upside up versus upside down. So, in your chair form, alpha glucose will have hydroxyl group there, Beta glucose will have hydroxyl group there, hydroxyl group there. Why does this matter? This matters because in beta glucose monomers, in order for any glucose to bind to other glucose, and I'm going to draw this way. In order for any glucose to bond to any other glucose, this will be alpha glucose, by the way. Both hydroxyl groups must be facing each other. They can't face away from each other. They can't be on opposite sides. If you have an alpha glucose and a beta glucose, for example, if this is your beta glucose, you're not going to get that interaction. There's too much distance between those hydroxyl groups. You need to have the hydroxyl groups be facing right next to each other for that interaction to happen. They have to be touching. They have to be in the same plane of orientation. They must be in the same plane of orientation. So, for alpha glucose, this is fine. They can all be in the same orientation, and it's fine. In fact, that's how you get amylose, an unbranched chain of alpha glucose, alpha 1,4 glycosidic bonds. This one bonds to this one, which bonds to this one, which bonds to this one, just continuing forward until you're done. But in beta, so we have beta glucose, and here we'll have our 4 carbon and our there. So we'll have hydroxyl group up versus hydrogen down. All right. In order for this to bond to another molecule, you have to flip the other molecule upside down. Flipping it all the way upside down. And then the next one can be flipped right side up. Oops, that looks terrible. Let's fix that. You have to flip 180 degrees. They have to be flipped 180 degrees in order for these hydroxyl groups to interact at all. That's why it matters. That's why it matters whether you have a hydroxyl group at the 1 carbon be up or down compared to the 4 carbon. Because if you didn't, you wouldn't, if you had them down compared to each other, you could just chain them together and it'd be fine. Every so often, with the alpha 1,4 glycosidic bond, the hydrogen bond, the hydroxyl groups that are down here will interact with each other and they'll polarize and they will have a hydrogen bonding that causes them to curve into a solenoid, and you'll have this slinky pattern form. That's a solenoid. But with beta glucose, these hydroxyl groups are 180 degree flipped from each other every time. So they will not interact. So they will zigzag and scatter into a perfectly straight line. So you get this fiber that is cellulose, thus fiber in your diet. That's why green leafy vegetables give you fiber, because the primary component in plants is cellulose, fiber. So, which brings us to the idea of the polysaccharide as an energy storage molecule. Alpha glucose is readily usable by animals as an energy source, as a source of fuel to produce energy for the production of ATP, excuse me. Starch. Starch is the energy storage in plants, and glycogen is the animal version of starch. It is energy storage in animals. Amylose is a straight, unbranched chain of alpha glucose. Unbroken 1,4 alpha 1,4 glycosidic bond, alpha 1,4 glycosidic bond, alpha 1,4 glycosidic bond, continuing on in perpetuity until, well, you're done. Amylopectin, however, is a firm texture. It is a starch that has branches. These branches occur at the 6 carbon, which is up here. So these 6 carbons, they are a 1,6, an alpha 1,6 glycosidic bond. So they will branch like so, and continue on with further 1,4 glycosidic bonds. So at the 6 carbon, you will have a 1,6 glycosidic